In general, when we have a related rate problem, this is kind of the structure of how I go about them. So when possible, I draw a diagram. I introduce notation, especially if something is varying with respect to time. I give it a symbol. We write out our information in terms of our symbols. So if we're told something like, height is varying at this kind of rate, rewrite that as a derivative of your height function. Then I think about what we want to know and write it out in terms of our symbols. So translate our question into symbols. Then write an equation that relates the quantities that we have in the problem. Once we have this kind of equation, we can differentiate both sides using the chain rule. Every once in a while, there's some sort of assumption in the problem that lets us get rid of some of our variables. But usually we can just go straight to differentiating both sides using the chain rule. Then we're going to calculate what I think of as snapshot information. So if we have, for example, a distance at a particular time that we're interested in, we can either work it out or include that information. We're going to substitute all of this snapshot information into our equation. We want to wait until after we've differentiated to include this information. And then we're going to solve for our unknown rate. Finally, you should think about whether or not your answer makes sense and does it match your intuition. In particular, thinking about whether the sign of your answer makes sense is an easy way to check to make sure that things are in good shape. So let's take a look at another example. We're going to try out this procedure. So take a moment and read this over. Okay, so what's going on here? We have a square, and we have that it's growing. And we're interested in finding the area, the rate of change of the area, when the area is 16 square centimeters. Okay, so first off, we have a little picture of our square and just arrows indicating that this square is growing. We're going to introduce some variables so that we can talk about what is changing. So E is going to be our edge length. In centimeters. A is going to be our area. And this is in square centimeters. We have a couple of constants. So we know, well, not really so many. Let's see. We know that our side lengths are increasing at a rate of 6 centimeters per second. And let's rephrase what we want to know in terms of our variables. So it says, at what rate is the area of the square increasing when the area of the square is 16 centimeters squared? So when it says, at what rate is the area increasing, this is asking for dAdt, the rate of change of area, when area is equal to 16 square centimeters. And let's think too about an equation that relates what we know about edge length with what we're interested in, area. This equation is area is equal to the edge length squared. Okay, so from this definition, this relationship, we can take derivatives. The derivative of A is dA dt. And we're going to use the chain rule to take the derivative of the edge length squared with respect to time. So our outside function is x squared, where our argument is equal to e. So we get 2e, and then we multiply by the derivative of e with respect to time, the derivative of the argument. All right. So this is a general equation relating rate of change of area with rate of change of edge length. We can even put in the information that we know. So what do we know? We know that dE dt is always equal to 6 centimeters per second. So dA dt is equal to 2e times 6. We were interested in dA dt at the moment when A is equal to 16 centimeters squared. And this is what I call the snapshot info. Okay. This is just a particular moment in time. So what we're going to do here is we are interested in the edge length when the area is 16 centimeters squared. Okay, and so let's figure out what that edge length should be. Our area is 16, and this is equal to e squared. So our edge length at that moment is going to be equal to 4. All right, and so plugging that into our equation, we get dA dt is equal to 2 times 4 times 6, or 8 times 6, 48 centimeters squared per second. Alrighty, and that was what we were interested in. Let's take a look at our sign. Our sign is positive. That means that our area is growing, which is what we'd expect if our square side lengths are growing. All right, great.